Hi, this is Michael Kogan. I'm doing my exam on the Doppler effect. Right now, I'll sketch out a little diagram to kind of explain what the Doppler effect is. Uh, it's pretty much just knowing that frequency and wavelength of waves will change. And this could be sound waves, electromagnetic waves, but they'll change with the speed of the source and the listener. You can kind of see it pretty frankly with, say, for example, the source. We'll say this one's the source. We'll say this one's the listener. Say that this one is moving towards this object. Uh, this direction will be positive. I'll go into that later with the formula. And this direction will be negative. But as this starts to approach the listener, the frequencies will start to grow because the actual wavelength will shrink. And as you go the other way, the wavelength will expand and the frequency will lower. That's just a quick little summary, but into the homework problems that I was given. So for part A, we were given a homework problem of a siren ambulance emits. So we'll write that as frequency S for source. Emits 2.8 0 times 10 to the third hertz. And that the speed, the velocity of the source itself is equal to 26 meters per second. And the speed of sound, which will stay constant, so I'll write this out on top, is 340 meters a second. Okay, so with this information, it wants us to figure out what is the frequency that you hear if you're standing in front of the ambulance. So to solve this, we will treat the listener as stagnant, and that S is moving towards the listener, which is in the negative direction. And so the formula in general, I have this memorized, but the formula in general is the frequency that the listener will hear equals V plus VL divided by V plus VS. And I say plus just because it's easier for me to remember the direction that they're traveling as a significant thing. But you can do plus or minus depending on what problem you want to set up. And then all of that times the frequency of the source. So just know we'll be using this now on for pretty much all of them. I think it's helpful to memorize it, but that's just me. So if we want the frequency of the listener, we'll set it up as this: equals 340, right? Plus 0, since the listener is not moving, and that's for the velocity of the listener, divided by 340, and this will be minus 26. And then all of that will be times 2.8 times 10 to the third power hertz. And I'll write hertz at the end just because the entire equation will be multiplied against hertz for the proper units, since I don't write down units as much as I probably should. And let me check the math on that one. Hold on, just plug it into my calculator. 340 divided by 340 minus 26 times 2.8 times 10 to the power of 3. For that, we will get 33.1. Let's see if listener equals 33.1.84. But we got to remember our significant figures. For this one, we are just using 3 significant figures, so that'll round off to approximately 3030. So 3030 hertz. Important to label. Sorry, I always forget. But that's the first problem done. with B. This one's asking for the wavelength of the problem itself. And that is a pretty easy formula. Sorry, I'm just double checking again on what the formula is. But it's a pretty simple formula of wavelength, or lambda, right, equals velocity divided by frequency, right? So since we have the velocity of the medium that's traveling through, remember that is the speed of sound, 340, we can take this formula and do 340 divided by 3030 to get, sorry, plugging it in again. I'd rather just do this with you so you can see that I'm just not making up answers. 0.11221. So since we're doing three significant figures, we'll just run that off to 0.112, and that will be labeled as meters. Okay, for the next problem. Part C is asking for what is the frequency that you hear if you're standing behind the ambulance. So remember our directions that we're going. So say, for example, the source is actually over here, and it's moving 26 meters. So I'll draw that out. So now this is the listener, and this is the source. The source is traveling this way, right? What is it again? 26 meters a second. And the listener is V is 0. So one way I always try to remember this is that listener to source is positive and source to listener is negative. So as we can see in this direction, that is listener to source. So this is positive. Okay. So here we will get the frequency for f of listener equals V plus VL, which will be 0, divided by V plus 26 times 2.8. 0 times 10. Now remember, I may have not written down the speed of sound in this specific occasion, but remember that's 340 meters per second. I was just not writing it down for sake of saving space. But just remember, whenever you see V without any subtext in a wave problem, it most likely is talking about speed of sound. Otherwise, people should label it as speed of string or speed of wave, whatever, right? So this will be 340 divided by 340, and then that'll be plus 26. So as already, our prediction should be, looking at this equation, that the frequency will actually drop and the wavelength will shrink. So it will be smaller on the wavelength. Things will be closer together. Wait, sorry, that's wrong. Wavelength will grow. That's on me. Sorry. I was thinking of shrinking in a different context there. Okay, but what we'll get for this is 2,601 hertz. And since we're using significant figures, we'll just round that off to 2,600 hertz. Sorry, I need to make sure to keep using my rough estimates for when we round stuff off. Okay, and then part D is pretty much the same as part B. It's just asking us for the wavelength of this. So I guess no more speculation on what I say. Wrong. We can see for ourselves what it is. So then we plug in 340, divide by 2600. Then we will see. 340 divided by 2600. 0.13074. So we'll round that off to 0.131. Right? Yeah. And make sure to label it as meters. I did label that as hertz. Okay. So we'll see it actually expands. Sorry. I was saying it's shrinking as a negative context. I guess I have a bias to higher frequencies. Okay, for E. A stationary bagpiper is playing a Highland bagpipe in which one reed produces a continuous sound of frequency 440 hertz. There is still, and the speed of sound is 340 meters per second. What is the wavelength of the sound wave produced by the bagpipe? Okay, so this is pretty much just asking right off the bat. So I'll still set up a diagram because I know there's a few problems after this that rely on this. But he's producing 440 hertz. So let's just write down all of our units. The frequency source is producing 440 hertz. Speed of sound is still 340 meters a second. And it's just asking us for the wavelength. So we know how to do that. Right? You take lambda, you set it equal to V over F. In this case, that will be 440 divided by, oh my gosh, I'm so sorry. That will be 340 divided by 440. Now that will equal, for this problem, for wavelength, it will be 1720 over 22, or 0.77272. So since we are rounding, we'll round to 0.773 meters. So see, this formula is very simple. It's very nice when we get a Doppler effect problem with this because it's really not complicated. The only thing that you need to keep track of is frequency and how it changes with motion. But this formula you'll always have. Okay. Now for problem F. I'm sure this will be more complicated. What is the frequency of the sound wave that a bicyclist hears if she is approaching the bagpiper at 10 meters per second? So this makes it a little bit easier. So we'll set this one as L and this one as source. The cyclist is approaching at 10 meters per second. The source is 0 meters per second. It's staying stationary. Okay, so we'll set up our little handy equation, right? Frequency of listener that you'll hear is equal to V plus V of L, and remember that is 10 meters per second, and since it's heading towards the source, that is positive. So 10. And then remember that the source is stationary, so we'll just divide by V, since it'll be plus 0, but I'll just save the writing for that. And then it'll be the frequency of the source, and that is 440 hertz. And I can set this like this so that it's still equal to. Okay, so what is 350 divided by 340? 350 by 340 times 440. So the total hertz be 452.9 since we're rounding. So let's make sure to keep those squiggly lines. I definitely have not been doing that. I'm so sorry. But it is 453 hertz. I don't know why I set that up like I was getting divided by something. So we'll round that off, but remember it's 452.94. Just gotta remember to keep sig figs. We're still at 3. C, D, E, F, G. So for problem G, sorry, I'm good at math, not at remembering my alphabet. Okay. For G, it's asking us what is the wavelength of the sound that the bicyclist hears if she's approaching the bagpiper. So we can take this frequency again, right? It's the same problem, our old bread and butter, right? Lambda equals V over the frequency, right? And it says we're taking out the listener. We'll take that frequency as a post-Doppler effect. So 340 divided by 453. And now for more calculator time, because I'm pretty sure you don't want to see me do long division. 340 divided by 453. 0.75055, and so on. Sorry, I'm looking at the problem. A slightly different answer. Let's head back up. Let's see. Should we make an error there? 4, 3. So we did not make an error here. So I'm assuming it's because I rounded off immediately. 40, 53, 0.7. Five, 0, 5, 153. Let me try this again one more time. Okay, there we go. Sorry for that little mishap. All right, I got 0.7728, but we'll run that off to 0.773 meters. So sorry about that. I made an error while calculating. Okay, so H. H is asking, what is the frequency of the sound wave that a bicyclist hears if she is moving away from the bagpiper at 10 meters per second? Okay, so let's assume for this diagram that the listener has passed, right? So this is now L, this is S. Uh, listener is now moving away from the bagpiper who's emitting these sounds, right? So the listener is moving away at 10 meters per second. So pretty much it's the opposite. So remember this equation? We can just flip the signs. That's all we need to do. So we can just flip the signs here. So we'll take f of L equals V minus 10 divided by V, 440 hertz. I'll find that on my calculator. Much easier to just flip it. 3, 4. Sorry, my dog's a little excited. We just got a new cat. But the new frequency will be 427.058. So remember, we always round off to 3 sig figs. We'll make that 427 hertz. I shouldn't say always. We're doing that specifically for this case right now for these problem sets, just because of how many values we're given. That was for H. So then we move on to I. We'll have to go to a new page soon here, but that's okay. What is the wavelength of the sound wave that a bicyclist hears if she's moving away from the bagpiper at 10 meters per second? So we basically just take this formula again, right? Just take this formula and we plug it into the lambda equals V over F. So we have 340. Sorry, I should be writing this down for you so you can follow. It was V over F, or aka 340 divided by 440. And then we get 0.7727, or, sorry, I'll set these equal, or roughly 0.773 meters. All right, and that's the answer for that one. Sorry for writing this down. It's instinct for math class. Next up, we have problem J. Problem J is, I am so sorry, my cat is coming on my desk. Problem J is, a police car is moving east of 40 meters a second. So sorry. Spilled my coffee. Thank you, Sarah. A police car is moving east at 40 meters a second, and it's chasing a speeding car moving at 35 meters a second. The police car siren has frequency 1.2 to 10 third hertz. So I'm going to just flip over to a new page because this is a lot of things we're going to have to remember, right? So let's start off with basics. Police car is moving at 40 meters a second. So that is f of s. Sorry. No, it's not. My cat scared me. F of s is 1.2 times 10 to the third hertz. The velocity v of s equals 40 meters per second. V of L equals 35 meters a second. And V equals 340 meters a second. So the first question it's asking is, what is the frequency of sound that the driver of the speeding car hears? So since V of S is heading towards the listener, both these will be negative. Since both these guys are heading this way, L, S, and this way is positive. Both those will be negative. Okay. What is the frequency of the sound that the driver of the speeding car hears? So then we just use our frequency of L equals V minus, this time because these are negative, 35 divided by V minus 40 times 1.2 times 10 to the third hertz. For that, we will get so in reality the listeners or the source is more just moving like 5 meters per second towards the guy if we just take in the actual reference frame. But sorry, I forgot to multiply by the frequency. It's 10 to the third power. We'll get actually exactly 1220 hertz. That's very nice. No need around. Okay, and that is for problem J. Sorry, I like to label these so I remember where I'm at. And for K, it's asking if the speeding sports car were to turn around and drive west at 35 meters per second towards the approaching vehicle. So now we're in a new scenario where this guy is going this way and this one is coming this way. Very dangerous. And it's now traveling at 35 meters per second towards the guy. So now this is positive. This is positive. And then this is still, of the source, is 40 meters per second. Negative. Very important to remember. So now our new f of L will be V plus 40, or sorry, 35 divided by V minus 40. And that will be times 1.2 times 10 to the third. Hold on 1 second. Sorry, I apologize for that. My dog was chewing something. I had to stop her. But as you can see, we have our equation now. So now we just need to plug it into our calculator. Should have done this off camera, but I don't want you to miss any steps I take here. So we can just use the same equation as before. If I can get my calculator working. We'll do 340 plus 35 divided by 340 minus 40 times 1.2 times 10 to the power 3. And that will be 1500 hertz. So we'll put that down there, and that'll be 1500 hertz. And no rounding needed. I like these problems. Okay, L. Part L is getting ready for the hard question. Part L is for a scene in action movie. A car drives at 25 meters per second directly towards a wall. The car horn is continuously and produces. The car's horn is on continuously and produces a sound frequency of 415 hertz. If the speed of sound is 340 meters per second and there is still, what is the frequency of the sound that the driver of the car hears reflected from the wall? Okay, so basically for this, we'll have this dot here as the source, this one as the wall, right? Whatever, right? I'm not an artist. And it is heading towards here, 25 meters per second. So this will be negative first, but then we got to also remember that when the frequency hits this, it's going to bounce back, and this will become the source. So let's first find out the frequency that the wall is going to hear. So for f of L, we'll set it equal to just V divided by V minus 25, since it is heading towards the listener, not the listener towards the source, times, what was that again? 415 hertz. And assuming that V, again, with no subtext, is 340 meters per second, include that the minus 25, that the new frequency would be 415. Sorry, I'm very slow at typing. 447 hertz. So we'll write down the full number here. 93, and then we'll round off there. Hertz. Now, this isn't actually a proper sig figs, but we're just taking this as the frequency the wall hears. Now, this is the new source frequency. So now, for our new f of L, which will be the car, it will be, this will be the source, and this will be the listener. So now the listener is approaching the source, right? So that will be positive. So then we'll have V plus 25 divided by V minus 0 times 415 hertz. Or sorry, not 415 hertz, our new value. I'll just write down 447.93 or 94 hertz. So 340 plus 25 divided by 340 times 447.94. First, I'll try just using sig figs. Oh no, I'll just put in the full number. So that will be 480.876, but since we need to go for sig figs, right? It'll be 480 or sorry, I'm so sorry. It'll be 481 hertz because we only do 3 sig figs. So this will be what the driver hears while traveling at that speed. We check our answer. That's correct, right? So then we go down to M, and M's a little bit more complicated. It's asking what is the velocity of the car if the sound reflected is 495 hertz, right? So you might get confused by that, but let's just look at our equation again, right? So let's set up two different equations. We'll do this as the listener, right? But that's really just the car equals V plus or minus, right? V of L divided by V plus or minus V of S times the frequency of the wall, right? And what's the frequency of the wall, right? we'll do frequency of wall equals V plus or minus V of L, and then V plus or minus V of S times the constant frequency that the car is producing. I'll just leave it as a constant, right? Just so that it makes it simpler. Now we can combine these two. Now notice that the frequency of the wall is the same as V plus or minus V of L, right? So let's get to plugging in the numbers, right? So let's see, the frequency of the listener is 495, right? Equals V plus, in this case, we got to remember this is when the sound frequency is going towards the source, right? So it'll be plus 25, or plus the V we want to know. So I'll put a naught in front of the speed of sound, so it's a little bit simpler to read. It'll be naught times V naught divided by V naught minus V, right? Times frequency, right? So then if we simplify that at all, 495 equals, and cancel out these two, right? V naught, V naught. So then it'll just be V naught plus V divided by V naught minus V times frequency. Okay. So you can also see that from the reference frame too, but I'm not smart enough to go into all that. So then we just got to solve this problem. So we can take 495 divided by the frequency, multiply it against V naught minus V equals V naught plus V, and I hope to God this is right. Frequency, and then here. After you do all that work, and the frequency, the base frequency is 415 hertz. Very important to remember that. Okay, after you do all that math for there, God, and you can multiply these out. Here, yeah, sorry. I just want to check to make sure my work was right, but I won't make any shortcuts. 495 over F times V naught minus 495 for F of V equals V naught plus V. So then we have 495 minus V naught equals V plus 45 V. And then you work all of that out, right? You multiply everything out. You get the actual figures. You will end up getting 29.8 901, right? All those decimals, but we'll round it off to 29.99 or 29.9 meters a second. And we can check, that's all right. So that's all the problems for the sixth problem in the homework set. I hope that all makes sense. I hope my explanation makes sense. All right, thank you.